In this video, we'll be working with a specific cubic equation of state, and more specifically, we'll be using the SRK equation of state, which was created by these three guys, Suave, Redlick, and Kwong. I'm sure I said those wrong, but we'll be looking at the specific cubic equation of state, and I'll be showing you guys how to put this equation into Python code or better Collaboratory. And to make some plots to better see the interactions between the pressure and vapor. Sorry, the pressure and the volume. So the very first thing that we want to do once we open our Collaboratory code is we first of all want to make sure we're connected, and we start off by creating a line of code. The very first thing we want to do is go here and copy and paste this website again, because we'll be using this once again in this throughout this code. So how do we put this in? We start by saying an exclamation mark git clone and simply command paste. You see cloning, and it is all into here. And as we can see, we can do we can go into here. We see that we have our CHE tools and so on, right? Cool. Alright, so now that we have this in here, we want to make sure that we have a path to achieve this stuff, right? We want to import it later on, so I want to make sure that it's all there. So we're going to do some more nitty-gritty stuff. So import system, import sys, and then do sys.path.insert, and then we open parentheses, one apostrophe of what we want. We want content CHE tools, right? Now we have that in there. And we also want to just simply simplify the CHE tools, so we'll simply import tools.che as CHE, as we've done many times before, just to simplify it out throughout the process. Now we can start off with our class, right? We can start off with our properties. So we're going to have P equals to CHE props for your properties, and for this specific example, we'll be solving for water. We'll be using it as our compound, but you are able to put whatever compound or molecule that you want into this. And then the end of the nitty-gritty stuff, I'm going to import. Last thing, we want to import numpy, right? So we're going to import numpy as np, right? And then now we're gonna from plotly subplots import make underscore subplots, right? So now here we go. There we have it. We have all of our nitty-gritty stuff all in together. We have all the kind of fundamentals ready, right? So now that we have all this nitty-gritty stuff, we are now able to start working this problem out, right? We can start solving it. So we can start by simply defining a function, and calling this function as the cubic equation of AB and ES, which stands for cubic equation for alpha, beta, for A, B, epsilon, and sigma, right? And then we'll be using for this is T, right? Because it remains same. And then for this we'll need a value for which A is equal to, value for which B is equal to, a value for which epsilon is equal to, and a value for sigma, right? And if we go back to this document that I was first looking at, and scroll down, and we can see that we have this kind of like this table of parameter assignments, and we also have some parameter assignments for the SRK equation, right? As you can see, we have SRK, and it gives us the values for the sigma and epsilon, so that we see that sigma is 1 and epsilon is 0, right? So you can go ahead and plug that in. So we said that sigma is 1 and epsilon is equal to 0, right? And if we go scroll back up, we can also see that it gives us an equation for A, right? We see that A is equal to psi times alpha, depending on two different values, then gas constant R squared times the critical temperature squared all over the critical pressure, right? So we can also go ahead and plug this in, right? So we can say that we have, I'm gonna send these all over now before it's too late. So we're gonna have A is equal to, we have psi, then we have psi times alpha times gas constant R squared. So we have alpha times R squared. Then we don't have an R. We haven't R, so we're gonna go up here right now. Say what the gas constants are. We know that is 8.314. It remains the same. So after the gas constant squared, we have the critical temperature squared. And for this, we're just going to simply put P dot Tc, which goes back looking over to the property that we put in right here. Right, so square this, and then we're going to want all of that all over the critical critical pressure. So we just do P dot Pc. Right. There we have it. We have the equation for alpha. Right. Right. There we have it. So now we also see that we have two other unknowns aside from where we have psi and alpha. So we're going to go ahead also have to give those some values, right? And if we go back over here, down to our table, we see that we are given these values. We see that for psi, S or K is constant. We have that psi is 0.42748. So we go ahead and put that in. So psi is equal to 0.42748. 4748. And then we also see that we are given the alpha value, right? We see that the A S or K is equal to this thing, right? And that is down here. So we're going to have to plug in this whole expression into our collaboratory code, right? So let's go put that in. So for alpha, we have 1 plus 0.48 0.48 right? 1 plus 0.48 plus 1.574 1.45 or was it 1.574 574, and this is multiplied times W, and we can also achieve this from our properties, so we're going to multiply that by P dot W, right? Right. Then after that we have minus 0.176, so 0.176, and then I'm going to multiply that by W, or P dot W squared, so square that out. And then that is also multiplied by 1 minus TR to half. So it'll simply be so then we'll have that multiplied by 1 plus or minus TR that to the power of 1/2. Right? And then we want to square that whole thing out, right? So another bracket and square. There we have it. We also have alpha in there. So now that we have that in, we also see that we have some other unknowns, right? We now don't know what TR is, so we're gonna have to give that some sort of value, right? If we go back to this table over here, we see TR does have a value. As you see here, it is given the value of T divided by the critical temperature, right? So we'll put in T divided by P dot TC, right? That's equivalent to saying the temperature by the temperature at the critical point, right? Now what else do we know, or what else can we put in? We're missing a B, right? We have everything else but B. So let's go back to our problems over here, and we were able to see that B is given an equation right here, 3.44. It's given as omega times R times the temperature divided the pressure, right? So let's go plug that in. So if B is equal to omega times this whole thing of the gas constant R times the critical temperature, which is just P dot Tc, and then we have both of those is being divided by the pressure at the critical point, which is P dot Pc, right? There we have it. But now we also have another known of omega. We don't know what that is, right? So we have to give that another value as well. And omega can also be given from this file back here. Just go scroll down to the original table. See that omega is a constant, SRK, and it's given as 0.08664. So let's go put that in 0.08664, right? 0.08664, right? So now we have all of our values given, and now we simply have to say we want to return A, B, epsilon, sigma values, right? And we push it in for shift enter. There we have it, right? There we go. So now that we have this whole thing put into our collaborator code, we can start defining another function and finding the value for P, right? So we're going to define a new function and we're going to call it cubic. Instead of ABES, we're going to call it simply P, right? This time, instead of just putting in the temperature, we're also going to put in volume, right? So B comma T, and then for this, we're going to use the AB, sigma, and epsilon values. So we're going to put AB, comma E, comma S. They're all going to be equal to the cubic of ABS T. This simply is just recalling that the AB and S values are dependent on this whole thing, right? And then after, we're going to want to return a P value, correct? So we're solving for P. Now, if we go back to this whole document, we see we go back to the cubic or generic cubic equation of state, and we plug this equation in for pressure, right? So we're going to go P is equal to, we're going to have gas constant R times the temperature, and then that is going to be divided by volume minus B, right? And all of that is going to be subtracted from A all over A all over V plus epsilon times beta, as well as V plus sigma times beta, right? And there we have it. We have put in our cubic equation for P. So now that we have all this actual stuff into our collaboratory code, we can now start plotting. We can now start making some plots, right? We'll start by giving off V for some given values, and we'll start off by simply linearly spacing the V values. So we'll do numpy dot line space. Then, as you know, the parameters from the start to the end and how many different points we want. If we go look back at here, we look at our equation, we kind of know the smallest and largest values of V, right? We know that V cannot possibly be equal to B, as that it would cause it to not happen. So we'll start off by saying that it is 1% larger than what B is. So we'll start by saying 1.01 times B is the beginning, and the endpoint, let's start at a really large factor. Let's say, 1 to the power of 6, 1 times 10 to the 6. And then let's say we want to make a total of 500 different points, right? Right. And if you can see, this has no clue what B is, right? Because we put B up into this function. So we're going to do is just simply copy and paste this B value into down here so that it knows what B is. Now it doesn't know what omega is, so we have to go ahead and put omega in as well. And there we go. Now we also want to go ahead and recall what pressure is. So we're going to go ahead and just put P is equal to, we set up here, we're just going to say P is equal to cubic equation P with volume and temperature. Right. Now we're also going to have to give it a specific temperature as well. And for now, we'll just start off to see how the plot looks, and then from there, if it looks good, we'll be able to make some different temperatures. But for now, we'll just start off with about 400 degrees Kelvin, and then let's make this sub-boss, right? So we'll have fig is equal to make underscore subplots. And then now we want to put in our scatter plot. So fig dot add underscore scatter. And we put our x and y value. So our x value is going to be our volume, and our y value is going to be our pressure. And then our mode, we're just going to use markers for now. Markers. Shift enter, and we get this horrendous looking graph, right? And you can't really tell much that is going on. It just seems pretty flat, and a lot of space missing. So one thing we can do to start to make this seem more and more like a graph, we can do, so we go fig dot update, and then we want to update our x-axis, and we're going to say as the type, we're going to change it into logarithm scale, right? Shift enter, and now starting to get this a little bit better of a graph. We see a lot more points, but still a lot missing between here, right? So now what we want to do is we want to add this change of logarithm scale to our lint space, right? So we're going to go in here because our beginning and end values are remaining comparative to the log of 1.01%. So what we're going to do is np dot log base 10 of this whole thing is going to be now the new start, and then it's going to end at np dot log base 10 of 1 to 6 times b. Now shift enter and we get this new plot that you can see is starting to look a little bit better, right? And we can now, since we changed this, this is no longer a line space, but we can now turn it into a logarithm space, right? So here's our new graph. Starting to get a lot more points, looking a lot better, starting to get a concavity is being seen a lot more as it changes, right? So now all that is sort of missing is the different temperature values that we want to look at, right? So instead of making it 400, we can now make it a for loop, right? So we're gonna have, instead of t equals 400, we're gonna have 4 t in the range, and what range are we gonna have? Well, I'm just gonna say start at the melting temperature for water, and let's say it goes up to, let's say, 800 degrees Kelvin, and we want 25 different points, 25 different temperatures. Now, what do we want in our for loop? Well, we definitely want our pressure to be in a for loop because it is dependent on temperature. We don't want to make a subplot every time, so we're gonna copy paste that and just add it up here. Right. Then this add scatter will we'll add it in here, but this, we don't want to update the axis every time, right? So let's see how it looks with the new temperatures. So you can see now we have 25 or 21 right here, different temperatures, and you can see it's still a little bit messy. There's a lot of stuff going on. Right now we have them still markers, and one thing we can do is start simplifying this with all the different temperatures. We can make this markers into lines. Right. Starting to look better. And we also see that this goes a lot off to the right, much more than we need to. So we can fix this. So instead of being 10 to the 6, let's make this 10 to the 4th. Okay. See it go down. Let's make this simply to the 1st. Let's see what happens. Okay. Starting to get nicer lines. Simply just put this whole thing as -2 for now. Let's see what we get with that. And there we have it. We have a little bit better looking graph, right? So you can see on the right hand side we have many different traces, but we don't know what these actually are. So what we're gonna want to do is we want to name these so we better know what each line indicates, right? What each line represents. So what we're gonna do is name, and then we're gonna use f function. We're gonna have the current symbol t, and then it's gonna be in Kelvin, right? So let me press Shift Enter, and then Right now on the right hand side we have all the different temperatures given to us in the actual Kelvin, not as just numbers, right? Now there's one final thing that we can do here to make this scatter plot look a little bit better. We can update the y-axis, right? We can see that this is kind of a bit messy. We can make this look a little bit better. So what we can do is another add update, but instead of the x-axis, we're going to update the x or y-axis. Then we're going to add a range, right? And this range is going to be, well, let's say negative 200 to 6 all the way to 200 e to the 6. Right. Shift enter, and now we see that we get this new graph, which is a lot more easier to read and a lot more satisfying to the eye. Right. So there we have it.